Hi class, in this video we are going to talk about the calculations of pH value for weak acid and weak base. So first of all, let's just talk about the weak acid. We have learned that weak acid will dissociate slightly or partially in water. So using the general formula of an acid, Ha, when it dissolves in water, it creating the H3O plus and A minus. So the Ha, if you represent this one as the weak acid, okay, so it will produce the conjugate base. So if you can refer back to the Bronsted-Rowley conjugate acid-base pair. So weak acid, after donating the hydrogen ion, you're producing a conjugate base. So the acid dissociate constant Ka is something that's similar like you writing the expression for Kc, Kp. So Ka, the A represent acid. So the Ka expressions depends on the equation. So products on the top, reactants on the bottom. So we have concentration of H3O plus because it's aqueous solution, raised to the power of 1, and then the concentrations of your conjugate base over the concentrations of your weak acid Ha. Remember that H2O is in pure liquid, so the concentration is constant and is excluded, or you don't have to include it in the Ka expression. So using another examples given over here, if you have a weak acid HCN, so we write at the bottom over here, this is a weak acid. So after donating the H plus, you get your conjugate base. So Cn minus is the conjugate base of HCN. So the Ka expressions of HCN, we have the concentrations of H3O plus, the concentrations of Cn minus as the product over the concentrations of HCN. And concentrations of liquid water is excluded. You don't have to write. So we say that if you have a higher Ka value, that means you will have the higher dissociation, which you will producing more H plus. So more H plus indicate that it has a higher concentrations of H plus. And when you're applying the pH equals to negative log concentration H plus, it gives you a lower pH value. So higher Ka, lower pH. Therefore, it is a stronger acid, or we have a higher acidity. So we have a formula for this pKa equals to negative log Ka. So Ka value normally it will be given in the questions, or you are requesting to find the value of Ka. So it's similar, pKa equals to negative log Ka. Higher the Ka value, lower the pKa value. Therefore, it has a stronger acid. Next, we say that a weak acid is generally having a smaller Ka value. It means that the dissociation is smaller, it producing less hydrogen H+, lower concentration of H+, slightly higher pH value of the acid, but still less than 7. So we can assume that the change in concentrations of weak acid is negligible. In order to calculate the pH value for a weak acid, there is a few steps that you can follow. So first of all, we need to write a balance equation. Remember, a balance equation for a weak acid is partial dissociate, which means you need to use the reversible arrow to write this balance equation. Second step, using the ICE table, fill in the content inside the table. Then write the Ka expression. Step number 4, calculate the concentrations of H+, and then you can apply to calculate the pH value. Right, let's just try questions to calculate the pH value of a weak acid. So in this question number 1, giving you the Ka value 2.35 times 10 to the power negative 8. Determine the pH value of a 0.20 molar acetic acid solution. So acetic acid has a formula of CH3COOH. So first step, write your valence equation. COH aqueous solution in equilibrium to produce H positive, and CH3COO negative, the conjugate base, also in aqueous. So initially you have 0.20 molar, and you don't have anything for the H plus and the conjugate base. So the change in the ICE table, yeah, initial change and equilibrium. Okay, according to the balance equation, we have a minus X for the reactant and then plus X for the product. So 0.2 minus X for the equilibrium concentrations of the acetic acid, X and X for each of your H plus and the conjugate base. So here is your Ka expression, where H plus on the top, we have conjugate base on the top as the product, and then over the concentrations of your weak acid. So in this case, value of Ka is given 2.35 times 10 to the power of -8. Concentrations of hydrogen is an X. Concentration conjugate base is also an X over 0.2 minus X. So in this case, you need to solve the quadratic equation. Okay, X squared, you got plus 2.35 times 10 to the power of -8, X minus 4.7 times 10 to the power of -9 equals to 0. You can solve it step by step accordingly. Okay, using the skills to solve the quadratic expression, and then figure out what is the value of your X. So in this case, X 6.85 10 to the power of -5, or a negative value. So this negative value, when you try to substitute into the ICE table, you get a negative concentration, which is invalid. Therefore, we will ignore the second value of X, which is negative. So in this case, we say that the concentrations of hydrogen is 6.85 10 to the power of -5 molar. So in order to calculate for your pH value, apply the formula pH equals to negative log concentration H plus. So fill in the value 6.85 times 10 to the power of -5, and you will get the value 4.16 for the acetic solution. So it's also proof that acetic acid is quite a weak acid because the pH value is quite high, but still lower than pH value. Okay, so the weak acid pH values is around 4, 5, 6. So here's the example of the calculations for a weak acid. So next, let's look at the calculations for the weak base. So we know that weak base will dissociate slightly or partially in water. So here is the equation. Okay, the B stands for the base. When it dissociates into water, it will in equilibrium producing the conjugate acid. Alright, so if in this case this B is our weak base, so after accepting the proton, it produces the conjugate acid. So the H2O behave as the acid, and after releasing the proton, it becomes OH negative. So the base dissociation constant Kb expression is as usual, product on the top, reactant on the bottom. So the Kb expressions, BH positive concentrations raised to the power of 1, OH negative raised to the power of 1, divide by the concentrations of your weak base. So similarly, the H2O, because it is pure liquid, so it is excluded from your Kb expression. So looking at the example equation here, we have NH3. So dissociate into water to give you NH4 plus your conjugate acid and OH minus. So the specific Kb expressions according to the dissociations of NH3. So we have concentrations of NH4 positive, concentrations of OH negative, and the reactant NH3 at the bottom. So H2O liquid is excluded. So if you have a higher Kb value, it means that it dissociates and releasing more OH negative. Okay, higher Kb value indicate that the equilibriums or the dissociations is higher, therefore producing more OH negative. Therefore, the concentrations of OH minus is higher and it gives a lower pOH value. Remember that if you want to know about pH value, we need to use pKw equals to pH plus pOH. So pH equals to 14, which is your pKw minus the pOH value. Therefore, we say that the lower the pOH value, the higher the pH value. You have a stronger base or a higher basicity. So the formula that we can use to calculate Kb, you can refer to this one, pKb equals to negative log Kb. So the relationship between pKb and the Kb, the higher the Kb, the lower the pKb. Therefore, stronger is the base. And we can say that a weak base generally has a smaller Kb value, and therefore we can assume the change in concentrations X is negligible. That means we can ignore it. So steps to solve the problem to calculate the pH value of a basic solution. First, same thing, we want to write the balance equation of the partial dissociations of weak base. Then we have the I stable, we have the Kb expressions, we have the concentrations of OH minus. Then we want to apply the formula to find pOH, and lastly, finding pH. So continue for the second questions examples. So in these questions, you are given a Kb value. Okay, so over here you need to remember that if you see Kb, it refers to the dissociation constant of a weak base. So determine the pH value of 0.30 molar ammonia solution. So you need to write out the balance equations that represent the partial dissociations of the weak base ammonia. So here you go, you got the NH3 aqueous solutions, and for weak base you need to add water, H2O liquid, in order to complete the balance equations. Okay, so weak base in equilibrium to produce the conjugate acid NH4 plus aqueous. Okay, so you add one more column on your order, and the H2O, after donating the hydrogen ion, it becomes OH minus aqueous solution. So the initial concentration for ammonia solution is 0.30. For water liquid, you don't have to fill anything in the ice table as the concentration is constant. Then the NH4 positive, your conjugate acid 0, OH minus also 0. So the change in concentrations according to the ratio of your balance equation, we need to minus 1x as this is the reactant. For the product, you just plus 1x as the stoichiometric coefficient is 1. Similarly for OH minus. So for the final concentrations or the equilibrium concentrations, over here you got 0.30 minus x, and then for NH4 plus, for x, OH minus, also x. So let's come up with your Kb expression, the expression for the dissociation constant of a weak base. So product on the top, we have the conjugate acid, NH4 positive. We have OH minus concentrations over the concentrations of your weak base. And then substitute the values. So Kb over here, we got 1.50 times 10 to the power of negative 10. Right, so looking at your ice tables, we will take this column. Okay, similarly like your KCKB, we're taking the concentrations at equilibrium. So at this one, Kb, it means that the dissociation constant, okay, after the weak base dissociate into the conjugate acid and the OH minus. So we have an X for the conjugate acid NH4 positive and X for the OH minus. And then for the concentrations of NH3, we have 0.30 minus X. So from here, you need to do your quadratic equation. Okay, so X squared plus 1.50 times 10 to the power of negative 10. This one you can do it on your own, yeah? And then we need to minus 4.5 times 10 to the power of negative 11 equals to 0. You may do it step by step until you get this quadratic equation, and then key in your calculators to get the value of an x. So you will eventually find out the value of x, 6.7 times 10 to the power of negative 6, or a negative value of 6.7 times 10 to the power of negative 6. Okay, since the concentrations cannot be a negative, so the negative values over here is not valid. Therefore, it will be ignored. So in conclusion, X is similar to the concentrations of OH minus. So 6.7 times 10 to the power negative 6 molar. And then we want to calculate for the POH value because you have the concentrations of OH minus. So calculating POH. So POH equals to negative log OH negative. And then substitute the values over here. Negative log concentration 6.7, 10 to the power of negative 6. So over here, your POH value equals to 5.17. Okay, and then finally, to convert it into the pH value, we are using 14 minus the value of POH. So final answer, the pH value of the ammonia solutions equals to 8.83. Which is slightly basic, but it's less basic, which is indicate well for this weak base. Okay, because the pH value is not that high, and it just slightly beyond pH 7.